I'm using nodal analysis, using the concept of supernode, find the current I in the figure. This figure, we have to find the current I. This is the current I, and then the method is nodal analysis. So before we proceed with Nodal, you remember if you have a problem on Nodal, you have to assign node voltages to each and every one of these nodes. So the first things first, you have to assign a node voltage to, or you have to pick a reference node, and your reference node would be a node that has more elements connected to it. So I'm going to pick this node because it has 1, 2, 3, 4 branches connected to it, and it's also located at the lower part of the circuit. So I'll pick this part to be my reference node. And remember, for your reference node, the voltage at the reference node is equal to 0 volts. So from here on, I'll pick other nodes and then I'll label them. I'll call this node V1, this very node V1. Then I'll also pick this node from here. I'll call this node V2. Then I'll pick this node above here. Here should be node V3. Then the next node I want to pick is this very node. Here should be node V4, right? So all the nodes have been picked. You might be tempted to assign node values to this or this, but remember that this and even up to this point, they are all on the same node. They have the same voltage, they are all the same potential. So same as this place and this place and the whole of this bottom part are on the same. So there is no need of assigning a special node voltages for this. So if we've done that, we remember that the voltage here is on ground, which is 0 because it's connected to ground. Remember here that the voltage here is 0 volts because it's connected to ground. The same here is 0 volts. The voltage here is V1 and so on and so forth. So let's write equations for these voltages. So we know that this 20 volts, 20, that's this, if you look at this voltage source, 20 is equal to the voltage at the positive side, which is 0, minus the voltage at the negative side, which is V1, right? So from here we'll conclude that our value V1 is equal to minus 20 volts. So that's the first thing. Then the next thing is we want to look at this source here. So that source is 15 volt source. 15 volt source is the same thing as the voltage at the positive side minus voltage at the negative side. So that will be V2 minus V3, right? Because the voltage at the positive side is V2, that at the negative side is V3. So from here we'll end up with, if we want to express V2 as in form of V3, that we want to express V2 as a in relation to V3, then we'll make V2 subject formula. If you make V2 subject formula here, you end up with V3 plus 15 volts, right? So that's our V2. How about this voltage source? This voltage source is 30 volt source, and that would be equal to the voltage at the positive, which is V4, minus the voltage at the negative, we can trace to ground, which is minus 0. From here, we'll get our V4 to be equal to 30 volts. So we'll keep this in mind as we apply KCL to the node. So from this diagram, we will see that the only missing term or the only missing voltage or unknown voltage is just V3. We don't know, we know V1, we know V4, but then we don't know V3. And once we know V3, we automatically also know V2. So the knowledge of V2 depends directly on V3, right? So this is what we'll do. We'll write node equations for at node V3. So write node at node V3 at node V3, that at this node we would have write KCL equation for that node. And before we do that, in the previous, because this is actually a correction to one of the previous videos I made, I went through the video and I discovered there was a particular slight mistake which led to a wrong answer at the end of the day. So I decided to correct that by making another video. So in that video, I choose the direction of current to be flowing away from the node. I'll still maintain that, and let's say current is moving away from the node, current is moving away from the node. You can actually choose it to move either away or into the node, whichever one, it's still going to give you the same answer. So for here too, current moves away from the node. Here too, current moves away from the node. Of course, here you know that current is moving away from the node already. So if current moves away from a node, we know that current enters through the positive side and exits through the negative side. Same thing here, current enters through the positive terminal and leaves through the negative terminal. Current enters through the positive terminal and leaves through the negative terminal, and positive terminal and leaves through the negative terminal. So we've assigned sign or polarities to each and every one of these voltage drop and then current direction. We do this assignment because of it aids in a writing of KCL equation at the end of the day, and then we don't end up getting wrong answers. All right, so by KCL equation for node V1, sorry, for node V3, we know that this current here minus this, that's the sum of this current, and this current, and this current, and this current equals to 0. That's by KCL, right? So apply KCL to that node. So what's this very current? This very current is the voltage at the positive side minus voltage at the negative side divided by the resistance, which is the voltage at the positive side is V3 minus voltage at the negative side is V4 divided by the resistance, which is 2, right? And then this is a negative current because the current is actually leaving the node, is flowing away from the node, so it's a negative current. So we are done with this current. How about this current? This current is also negative because it's leaving the node, and that will be, what will be the value of that current? It's going to be the voltage at the positive, which is V3, minus voltage at the negative, which is V3 minus the voltage at negative is 0 divided by 4 kilo ohms. Then minus, how about this voltage? Sorry, this current here. That current is going to be V2, the voltage at the positive minus voltage at the negative, which is V2 minus 0 divided by 1. Then how about this current here? The current drawn from this branch is equal to the voltage at the positive. It's negative because it's also leaving this very node. That will be V3 minus the voltage here is V1 divided by 3. And how about this very one? That would be minus 10 milliamps equals to 0. We don't need to do any algebra for this because the value of the current is known. And remember, these are current, is current, is current, this is current. So all these values are current values. So from here, we simplify our expression. That will be minus V3 minus V4. So V4 from here is equal to 30. So I'll just say minus 30 because the value of V4 is 30 from this expression, all divided by 2, then minus V3 divided by 4 minus V2 over 1, then minus V3 minus V1, right? V1, what's the value of V1? Sorry. Oh, yes, what's the value of V1? V1 is minus 20, so it's minus 20, 20, then divided by 3, then minus 10 equals 0. So what I will do to simplify this expression is to multiply each term here by the LCM of the denominator. So we'll clear out the fraction. So if you multiply through by the LCM of the denominator, which is 12, the LCM of 2, 4, and 3 is 12. So that will be 12 multiplied by V3 minus 30 divided by 2 minus 12 multiplied by V3 over 4 minus V2. Now in V2, from here, V2 is equal to V3 minus 15, sorry, plus 15 divided by 1. Then we are multiplying that by 12, right? Because I'm multiplying here by 12, by 12, by 12, all through. Then here you have minus V3 plus 20 times 12 over 3, then minus 10 times 12, right? I'm sorry, I wrote above the line or beyond the line, but then I don't have a choice than to do that. So 12 divided by 2, that's minus 6 into V3 minus 30, then 12 divided by 12 divided by 4, that would be minus 3 V3, then minus 12 times V3, that will be minus V3, sorry, minus 12 V3, then 12 times 15, and then you have minus 180. Then 12 divided by 3, that will be 4. 4 times V3, you have minus 4 V3. Then my 12 divided by 3 is still 4. 4 times 20, you have minus 80. Then minus 10 times 12 will give you 120, everything equals to 0. So open the bracket, you have minus 6v3 minus times minus is plus 180, then minus 3v3 minus 12v3 minus 180 minus 4v3 minus 80 minus this is going to give you minus 200 equals 0, right? Minus 200 equals 0. So add this and this together. This plus this is 9. 9 plus 12 is 21. 21 plus 4 is 25. So you have minus 25 v3. 180 plus 180 minus 180 will go, then minus 200 is equal to 0. So you have v3 is going to be 200 goes the other side, comes 200 divided by minus 25, which is equal to minus 8 volts, right? So we've gotten our v3. So from v3 we can now easily get the value of this current here. How do we find the value of that current? We apply Kirchhoff's current law. Kirchhoff's current law at this node. The by KCL at the ground node, we have this current I that is entering is positive, so we have I, which is positive. Then this current that is also entering this very node, I'm talking about applying it at this node, this is also entering this very node, so that will be plus. What's the value of that current? Voltage at the positive minus voltage at the negative divided by the resistance. What's the voltage at the positive side? V3. So you have V3 minus voltage at the negative side of that is 0 divided by the resistance 4. Then this other current that passes through this voltage source, because this current is the same thing as the current passing through and enters this node, since it's entering is positive current, then what's the value of that current? That will be the voltage at positive minus voltage at negative divided by 2 kilo ohms. So that will be, from here you know that is V3 minus V4 over 2. So that's V3 minus V4 divided by 2. Everything equals 0. So I from here plus V3. What's the value of V3? Minus 8 divided by 4, plus here you have minus 8 minus V4. What's the value of our V4? 30 divided by 2 equals 0, right? So from here you get I to be equal to, or I minus 8 divided by 4, that's 2, then plus minus, how we minus 8 plus 38, 30 will give you 38. 38 divided by 2, that will be 19 equals 0. So I would be equal to, take this to the other side, 2 plus 19, which will give us I is equal to, if you add 2 plus 19, you get 21 milliamps, right? So that's the final answer to this question. So take a look at this, take a look at the question, these are the solutions and every other thing. So like I said, this is just a sequel to, or a correction to, my previous video. If you check, this is that video where the final value of I was this, but then it was a mistake because I made a mistake around here, right? If you evaluate this should actually be plus, not minus, but then I had that mistake, so I'm correcting it. So thanks for watching my video, and sorry for the mispresentation of my answer. Sorry for not actually going through it before posting it, but then I promise that won't repeat itself in the future. Thanks for watching and have a nice day. Please subscribe to my channel, like, comment, and share these videos to your friends in school so that they will also benefit the good things and the free tutorials you've been having. Thanks. Have a nice day once again.